right. Welcome back, guys.
Thank you for welcoming us back.
We are trying to figure out how chemical bonds actually work. We are slowly making progress through our notes here. Okay, so this is a little review of, we have lots of different ways of thinking about orbitals and bonds, but we need to reconcile some problems that we talked about. So yesterday we talked about how if this is true, then we should have all of these stable compounds in existence. Two of them don't exist, so that's kind of weird. Okay, and then to illustrate our hypothesis, we had this. So we're hypothesizing that I just take the orbitals and they just overlap, and that's how I form a chemical bond. Okay, and that's all well and good, but I end up with bond angles that don't make sense, and the fact that these compounds exist doesn't make sense, and then on top of that, the fact that all of the bonds in each of these molecules are identical, the same strength, the same length, also doesn't make sense. So what the heck? So okay, so I actually added this slide, okay, so just to be a little more specific, okay? So, for methane specifically, we expected carbon to do CH2, it does CH4 instead. We expect it to be a 90-degree angle, and then this is what happens. We have this bond angle, and all of the bonds are identical, okay? Whereas, let me just illustrate real quick, okay? So, where are the valence electrons for carbon? What subshells are they in? Which S?
S2.
2S and the 2P.
Yeah.
All right, yeah. So my S subshell looks like what?
Circle.
There you go. There's 2S. What does 2P look like?
It's like the... Yeah.
3 dumbbells at right angles, right? Yeah? So if carbon is going to make 4 bonds, our first prediction would be something like this, where maybe I have a hydrogen overlap with that P, and that makes a bond, and then we have a hydrogen overlap here, and then a hydrogen overlap there, right? So there's 3 P orbitals, and I could overlap there, and then if I want a 4th hydrogen, the only other valence electrons are in this S, so somehow this and this have to overlap, right? Somehow a 4th hydrogen has to fit in there and overlap with that S orbital, even though there's all these other orbitals in the way. Okay, so based on this prediction, these 3 bonds should be very strong, right? Because we have good overlap, and then this would just be like maybe a very weak bond and maybe a different length. Okay, but so this is the prediction. But this is what I'm saying happens. All the bonds are identical. Okay, when you do a spectroscopic experiment and measure the dissociation energy and all that good stuff, they're identical. Okay, so this is just highlighting that this can't be right. Okay, the angles are wrong. These should all be 90 degree. They're not, and the bond strengths and all the data doesn't support this hypothesis. Okay, so we need a new hypothesis, which is called what, or involves what? Do we remember from yesterday? Hybrid orbitals, okay? So we come up with a new hypothesis that could explain the evidence, okay? And so we have these orbitals to begin with, okay? These are the ones that I just drew. What do we do with them? Combine them. And by combine, we're doing that mathematically, okay? We are not going to do that in this class. Okay, I even tried Googling it, and it was hard to find. It's in a textbook somewhere. I will find it in one of my college textbooks. Anyway, we do a bunch of math. Ooh, magic math. Okay, and we end up with new orbitals. And conveniently, we end up with 1, 2, 3, 4. Hey, that's perfect. That's exactly the orbitals we need. Now, so the other thing is that the math does not, and this is what my textbooks were reminding me of, is that the math does not tell you the angles of the orbitals. It just tells you the energy and their shapes, and maybe some other stuff. So if I understand this correctly, we get to just make up whatever angle we want, and that's literally what we do.
But
Don't they repel each other?
Yeah, so they
try and...
furthest away.
Yes, according to Vesper theory, valence bond theory, and if I look at the mathematics of it, does not tell me these angles. I'm taking two separate theories and using them at the same time. So I'm using valence bond theory to give me these orbitals, the hybrids, and then I'm using Vesper theory to assume they're at this angle that matches my data. That's my understanding of it. It's a little shady, but that's the best we have. Yes?
Did you ever get like what orbitals were actually combined together?
Well, I know that these is one s orbital and three p orbitals. In terms of how they were combined, I was trying to find that and I haven't found it yet. I'll let you know.
We would you combine the s orbital with each of the three p orbitals to get 3, right? But then how do you get the fourth one?
Oh, yes. Yeah, I'm not sure. I still need to look that up. I will
So we
fit.
just combine orbitals right now.
All I know, yes, and it could even, and I said yesterday that you combine them like in pairs. That might actually have been wrong. I need to go double check that to make sure that that's even correct. It might be that, yes, I'm not even gonna speculate, so I'll find it, okay? But yes, so anyway, Linus Pauling is the one who's famous for proposing this hypothesis, okay? And so, hey, look, we have a way of kind of creating 4 identical orbitals that can then overlap with the hydrogen's orbitals and we get our methane. So it works, okay? So this is at least consistent with what our evidence is showing us, okay? So if I wanted to visualize this, if I take all 4 of these, right, and put them together, this picture kind of hides the little other piece that's hanging on there, okay? But this picture actually shows it. So now I have these new hybrid orbitals at the angles that I need them, and they can overlap with my hydrogen unhybridized orbitals. So these orbitals are the same. This is just a 1s orbital. They overlap, and I create my bond, and I get my tetrahedral shape.
Isn't diamond that shape? Like it's just if you replaced all those hydrogens with
Maybe.
Remember?
Can't
like
remember.
It's a crystalline like pyramid.
It's something like that. I can't remember if it's tetrahedral or not. I think it might be.
Because I think
Carbon's
that's
a
why,
wild. Carbon can do all kinds of wild stuff.
Yeah, but
Yeah.
I'm pretty sure that's why they cut diamonds like they do.
But it's
because
not
it
just.
helps emphasize the crystal structure.
I think they cut diamonds because it refracts light in a way that makes it shiny. They just want it to look pretty.
It's not just carbon that does it though, right?
Does what?
The hybrid.
Yeah, no. Any atom theoretically can do this. Maybe except hydrogen.
But only the central atom.
But we're only doing the central atom. Yeah, so that's a point that I'll emphasize on a later slide. We only hybridize the orbitals on the central atom.
Can you have multiple central atoms in a molecule?
Yes, yeah, and we will have some examples of that. Yeah. So, no, but the diamond thing was a side note. But yeah. Okay. We okay so far? Okay, so let me kind of explain a little more what's going on with these hybrid orbitals. Okay, so here's my definition. Okay, hybrid orbital, I'm not gonna have you memorize this, I'm just putting it there for you to have. Okay, so we're mathematically combining orbitals that we already had. Okay, and so another thing that's important for this is that in order for the bonds to be identical, we need these orbitals to all be the same energy. We all remember that S and P are not gonna be the same energy because they're different subshells, yes? So if I'm gonna make 4 bonds of equal energy, well, then my orbitals need to be the same energy. And so the hybridization process accounts for that, and it basically gives us an average of these energies in the new hybridized orbitals. And it's technically a weighted average. Okay, and if you want to read my college textbook, one thing that it emphasizes is that the total energy we started with is the same as the total energy we ended with. So this math magic that we're doing here is not breaking any laws of thermodynamics or conservation of energy like that, okay? Because if you come up with a theory that assumes that energy is created or destroyed, it's probably wrong. So we don't want to do that. Okay, so we're still accounting for the energy.
Are we going to be
Okay.
using that like notation, the SP superscript?
Yes, and we'll talk about that. Yeah, so you could probably guess that if I take one s orbital and 3 p orbitals and combine them, we just name the new orbitals sp3. That's an sp3, that's an sp3, that's an sp3, that's an sp3. You just name the orbital from what it was made from. Okay, so now if we're looking at this, this makes sense. Oh, I have 4 orbitals with each unpaired electrons. It makes sense I could now take some other orbitals, like my hydrogens that have an unpaired electron, right? And if they overlap, I can get 4 bonds. Okay, so this is how we're making sense of all this, okay? Here's the weird part. Hybridization is math that we did or we do to explain the evidence, but we don't have necessarily, there's no reason to believe that hybridization is physically happening on the actual atom. Okay, so it's not like there's a carbon atom sitting with its normal orbitals and then some hydrogen is coming, it's like, oh, we're about to bond, change up the orbitals, and they mix together and you get new orbitals and then they overlap. It's, we know that carbon bonds with hydrogen, and we need to describe the bonds and the orbitals somehow, so we come up with a mathematical description of it, but is that literally what happened in the physical world? Nobody really knows. We're just coming up with a way to explain the evidence, but we can't necessarily prove or figure out what is physically happening. Okay? This is kind of the unsatisfying part of quantum chemistry and stuff at the atomic level, is we can see what it does and we just have to come up with a way to explain it, even if we don't necessarily, like, we can't watch it happen in real life. We just see the before and the after and we just kind of make up a way of how it got there. Okay, but this may or may not be actually what's happening. Okay, so it's not like a literal process, it's just math that was done to explain how we ended up where we ended up. Okay, and so here's the point that was brought up. Okay, so we're only doing this to the central atom. Ouch. That thing always falls. Questions about that? Crickets. Okay, so just to clarify, sp3 are not the only hybrid orbitals that exist. We can combine lots of different orbitals to make the number of bonds that we need, okay? So if I had an s orbital and combined it with one p orbital, which I'll show you when we would use that, we'd call that sp. If I have an s with 3 p's, I call it sp3. There's sp2, I skipped that, okay? You just name it based on what it came from. Okay, and we're gonna go all the way from sp all the way up to sp3d2. Okay, and I don't know if this is on any of my slides or not. Okay, the number of orbitals that you start with is the same as the number of orbitals that you end with. So with sp3, I needed to make 4 bonds, and so I needed 4 orbitals to make each one for each bond. So the number of orbitals that you start with is going to equal the number of orbitals you end with, and will be equal to the number of electron groups on your molecule. Okay, I'll do a bunch of examples to explain that. So for example, for methane, it needs to make 4 bonds, and so it needs 4 orbitals in order to be hybridized to make those hybrid orbitals. Okay, if I had something that was trigonoplanar like this, in this case, boron needs to make 3 bonds, and so it's going to have 1 s orbital combined with, so that would be the sp2, I don't know why I skipped that one. 1 s orbital and 2 p orbitals will combine to make these. Okay, I have a chart on the next slide. Okay, but the number of orbitals that I combine is equal to the amount of bonds or lone pairs that I need. Okay, I'll show you a bunch of examples, but I'm just mentioning it now.
The last one, it should be 1s and 3-2, right?
Yep. Thank you. So this is just explaining how we name them. Okay, it's a pretty simple naming system. Cool, keep moving on. Okay, so here we go. Let's make it, I got a little table just to kind of summarize what's going on. Okay, so if I am in a situation where I need 2 hybrid orbitals, okay, that would always be an sp. If I need 2 hybrids, then I need to use 2 atomic orbitals to make those hybrids. Okay, and as a quick review, if I had two orbitals making bonds, what shape do they make if two bonds want to repel each other? Linear. Yeah, looks like that. So this is a situation where I had one s orbital and one of my p orbitals combine, and then I get an sp orbital and an sp orbital.
So one S and one P orbital make two SP orbitals?
Exactly.
Alright.
Exactly. A fancy way of saying it is the number of orbitals is conserved. I started with an S and a P, I have two orbitals, I combine them and I get an SP and an SP. I still have two orbitals. Okay, the number of orbitals is always conserved. Okay, so an example of that happening would be like beryllium bonding with chloride. Beryllium chloride would do that. Okay, if I need 3 hybrid orbitals, then that means I have an s orbital combining with 2 p orbitals, and so that's sp2. Three electron groups makes what shape? Trigonal planar. Sounds about right. Looks something like that. BF3 is a good example of that. Okay, and then we talked about sp3, right? I took one s orbital, 3 p orbitals, I combine them, I get a tetrahedral shape, looks something like that. Okay, methane was our example for that.
So for the fourth one, you would call all of those orbitals sp3?
Right, exactly. This is an sp3, this is also an sp3, they're all the same type of orbital, so they all have the same name. So wait a second, let me back up. So here, if I had an S and a P, right, there's still 2 other P orbitals that didn't get hybridized. What happens to them? Nothing, they're still there. So, right, because before, right, I had my S and then like 1, 2, 3, these are my P orbitals. If I want to make an SP hybrid, I only need to combine these 2. I still have 2 other ones that were untouched. So there's actually 2 other p orbitals that are still there, unhybridized.
So what's the significance of that? That means they can carry 2 more bonds?
Sure, it's a spot where electrons could be, it's a spot where I could make more bonds. We'll talk about multiple bonds probably tomorrow or the day after that. Okay, but I'm just saying that like if I don't here, I took an S and then a P subshell and I combined them all to make a hybrid. If I only combine a few of them, those other 2 orbitals still exist. Whether or not they have electrons or are doing anything is a separate question, but they're still there. Okay, so here I had my S and then P, sp2 means I combine those 3. I still have a p orbital, and I don't know what direction it's pointing, but it's somewhere on there. There's still a p orbital. Okay, so they don't just disappear into nothing. They're still there.
But the electron geometry only goes off of the hybridized one?
Right, the electron geometry is only for orbitals that have electrons in them. Those unhybridized orbitals are empty for now, okay, unless we find another situation where they're not.
Because there's no active bonds there? Is that why?
There's no electrons in them.
Oh, just straight up, okay.
Right, yeah, and then you could have the weird philosophical conversation like if there's no electron, is there really an orbital? Like, but it's like, it could be there, I don't know. If a tree falls in the woods. Okay, if I want to make 5 bonds, what comes after P? We're going to throw in a D orbital. So I'm using 5 atomic orbitals to make 5 new hybrid orbitals. If I've got 5 orbitals arranging themselves to make 5 bonds, what shape does that make? Yeah, trigonal bipyramidal, which looks like that, but you already knew that. 3 of them make a triangle, right? Those are the equatorial ones, and then I've got 2 going straight up and down. Those are my axial orbitals. Okay, PCl5 is a good example of that. Okay, and then the highest we're gonna go, I mean, it goes, you can go crazy, you can go even higher than this, but we stop at 6. Okay, I would need another d orbital. If I needed 6 hybrid orbitals to make 6 bonds, what shape do I get from there? What is it? What is it? What is it?
Octahedral. I was
Yeah.
just saying that.
I heard you thinking it. Octahedral, okay. And our classic octahedral molecule is sulfur hexafluoride.
Isn't that weird that it's 6?
Say what? Okay, sorry.
Why is an octa prefix for 8?
It has 8 sides.
It has 8 faces.
Oh, but it says 6.
8 faces.
Yeah, so we have to go back to our D&D dice to remember this. Is that this is an octahedral shape. It has 6 vertices, so each of these is one of the pointies on here, but the shape is named after how many faces it has. It's 8-faced. Yeah, kind of weird, but yeah. So it's octa, but 6 points.
What about tetrahedral one?
Tetra is 4 and 4, so it just works. It's convenient that way.
No, like what's like the 3D shape you would think?
Oh, this.
Oh, it's just a, oh.
It's like a triangle pyramid. Yeah, 4 points, 4 faces. Yeah. Kind of cool. We okay with this? All right. Okay, so summarize. Here we go. So in Lewis dot theory, we were assuming that we make bonds with unpaired electrons. Okay. In our new theory that is more detailed, we are still using that assumption. Okay, we are still taking unpaired electrons and pairing them up to make bonds, but we are now thinking about them in terms of orbitals
And not electrons.
and not just electrons that are just dots. It's like it's an electron in an orbital and the orbital is now involved. So we're just thinking about it in more detail. Okay, I'm not telling you this is wrong. I'm just saying it's oversimplified. This is the cartoon version. This is the more realistic version. So chemists still use both of these, but they understand what they're using when and all of that. Okay, and then the only thing we're adding to this is that now, in order to make this work and be consistent with experimental data, we need to introduce this idea to make it work. Okay, but this fundamental premise of we make bonds with, I have an unpaired electron, they need to be buddies, that is still how we think of bonds. We just had to modify our orbitals to make that still work in our brains and be consistent with the evidence.
But this is like actually true. Because you said that like we don't know how it happened.
Right, if we do the math and we get our hybrid orbitals and then we compare that to the evidence, it is consistent for the most part. There's a few things that are unexplained by this, which is going to lead us to the next theory next week. There's another theory that is even more gory detail than this, that is the most accurate, but it's the most complex. Okay, but this explains more than this does, right? So it's just, we're improving as we go.
So the part that wasn't like literal, as you said,
Yeah.
that's the actual process of hybridization, but the actual
Right.
shapes are present, right?
As far as I know.
Okay.
I feel like I'm gonna tell you the opposite of what I just said next week, but yes, there's multiple ways. It's weird. There's multiple ways to think about bonds, and they are all correct in different situations. So it's a very gray, nuanced kind of thing. That's the best way I can explain it. We don't have one theory that explains all bonds always. We still don't. And so this is kind of an unperfected aspect of chemistry, is like we can explain bonds pretty well, but we don't just have one theory that explains everything. We have different theories that explain different parts of how bonds work. And then by using all of them, we can pretty much cover all the bases, but we don't have one theory that explains
So
everything.
is there like a more advanced form of the Lewis dot theory, or is the Lewis
That's
dot
this.
theory? Okay, so they both, okay.
The way I think of it is different levels of like complexity and how specific you're doing it. Like this is the 8-bit version, this is the 1080 version, and then we're gonna do the 4K version later. It's like it's all bonds, but it's like how specific do you want to be? So, all right, there we go. Cool. I think we have examples. Yes, let's do some examples. Okay. So let me walk you through an example of what I'm going to be asking you to do, okay? So what I'm going to do, in some cases, I'm going to give you a molecule, and I want you to tell me what type of orbitals do I need, aka what type of hybrid orbitals do I need in order to make all of these bonds work. Do I need sp orbitals? Do I need sp2, sp3, sp3d, or sp3d2? Right? We have 5 types of hybrid orbitals. What type of orbitals do I need to make that molecule work?
SP3, right?
Maybe.
SP3D.
Don't shout it out.
It could be sp3. The one thing I kind of said I wasn't super clear, if I have a lone pair, I also need a hybrid orbital to account for lone pairs on the central. Yeah, so maybe add that as a side note. So let me give you some steps. The first thing we want to do is just draw the Lewis structure. Okay, so I've got 3 steps that if you get lost on a worksheet or in some problems, these are the steps that will help us figure this out. Okay, so step 1, draw the Lewis structure. I'm gonna do this off to the side and you guys can tell me how to do it, or you can do it and tell me the answer. See if we can do this real quick. What's the structure for SF4?
S is in the middle.
S is in the middle. I like it. F's are probably around it. Okay, good start. Got the skeleton. They're probably got at least one bond. How many electrons are we working with?
No idea.
8 times a lot.
16.
Sulfur has 6. Fluorine has 7 times 4. 34. Let me just slap 8 on everyone and see how we're doing. 8 times 4. 8 times 4 is. I'm missing some electrons.
Give sulfur to.
Yeah, let's give it to sulfur because sulfur can do the expanded octet thing.
That's right.
Bam, that's our structure. Okay, so we're good. So that's our first step. We just want to draw the cartoon version of the molecule. Okay, then we're going to predict.
It would be trigonal bipyramidal.
Yeah, trigonal bipyramidal. And the molecular, this is C sub.
Why do
How do you know that?
Hmm?
Why do we need
So we're kind of doing 2 things at the same time. The Vesper theory will match the hybridization. They correspond, even though they're separate theories.
Hybridization would be SP4 then, right?
SP4 is not a thing.
SP3?
Or yeah, SP3D.
Right, we need 5. Okay, yeah. So just to get everyone up to speed, if I look at sulfur, I have 1, 2, 3, 4, 5 electron groups. Right? A bond or a pair of dots counts as an electron group. That's a group, that's a group, that's a group, that's a group, that's a group. Right? 5 groups, yes? So that's trigonal bipyramidal. Okay, and if I go from sulfur by itself to sulfur bonding like that, I need 5 hybrid orbitals in order to make my 4 bonds in a pair. So if I need 5, 1, 2, 3, or 5, I need to start with 5 orbitals, okay? So I take an S, I'm gonna use all 3 of my P orbitals, and that's only 4, I need another one from a D subshell. 1, 2, 3, 4, 5. So I need those 5 orbitals from sulfur to be hybridized to make the little homes for all those electrons to live in. So what should I name an orbital that was made from 1 S, 3 Ps, and a D?
SP3D.
Just name it what it was made from. Those are the type of orbitals that are housing these bonds and those electrons. That's the hybridization of sulfur in SF4, sulfur tetrafluoride.
So is the addition of D subshells why things above a certain area are able to have? Yeah, okay.
That was the original explanation for expanded octet, right? Because it has D orbitals. I keep saying this, but I could give you some sources that say that that turns out is not entirely true. I don't know exactly what the perfect explanation is, but yes, that was an early explanation and may or may not be accurate.
Oh,
So
gotcha.
this is the part of the course where I'm like, I don't know, it's a lot going on that I can't fully explain. In other chapters, it's like, yes, it's very definite, but this is not, we haven't fully figured this out. Like right now in history, in the scientific community, we have not fully figured all of this out. So it's like, it's literally still a developing, yeah, it's quantum, there's all this crazy math that we can't see it, it's too tiny. Okay, but this is as far as we've gotten.
Are we waiting on technology to catch up at this point?
Could be technology, could be wait for someone to be smart enough to figure it out, but the guys who figured this out were like pretty stinking smart, so I don't know what the holdup is, honestly. I'm just a high school teacher.
Wait, so how does sulfur have a d subshell? A d orbital?
It has it in its cloud in general.
Yeah.
They all have all of them, they just fill up.
Oh, they just fill up
specific
each,
ones.
okay.
Right?
Because like its electron conflict stops at 3p, right? So it just has a d orbital that's unused, is that?
So this is the part of the theory that is still contested today when you get into the D subshells.
Because-
I could give you part of my book where it's like some people think this is wrong. Okay, but where it's definitely more right is with the SP3. Up to SP3 is like widely used, and there's a lot of data to support that. The D part is like, okay. So stay tuned for developing discoveries in the chemistry field. Okay, let's do some practice. Try this one on your own. Okay. Last slide for today. What kind of hybrid orbitals do I need? Put chlorine in the middle.
Is that a plus on that?
Yeah, it's a plus.
Alright.
So here's our skeleton. I think that's just it. And then the plus is probably the formal charge on that central chlorine. That's probably what's going on there.
Which is irrelevant to this.
Yeah, yeah.
How do you get formal charge again? Is it like what it is?
You take
now?
it's the neutral atom minus
What it okay.
what
so
it has
it's-
here.
Okay.
So 7 minus 6. 1, 2, 3, 4, 5, 6. Bonds count as half for formal charge.
7. Can fluorine not be central?
No.
Is that?
So it's tetrahedral.
this would
For
be
other
SP3,
reasons besides formal
right?
charge and stuff, it's usually not the central atom.
Just for fluorine.
Yeah.
It's tetrahedral because there's 4.
Yeah, okay, so if we're looking at our electron groups, 1, 2, 3, 4 groups, tetrahedral. Tetrahedral is 4 electron groups, okay, so I need sp3 orbitals to make this work. 1 s, 3 p's gives me 4 orbitals, okay, so these orbitals are sp3.
So, Mr. Floyd, how
Yeah.
does, like double bond play into that?
Double bond, great question, that's tomorrow.
Ah.
That's the next lesson, yeah. Because we're gonna have to figure out how double bonds work with this, yeah.
Would it not just be another circle?
Chloride, a stable.
Right, but it is no, because according to
They
what
go in the same circle.
right, but the question we want to answer is what happens to the orbitals. Okay, this is the cartoony version where I'm just drawing lines, but what happened? How do I do that with orbitals? That's the question we'll answer in the next one. Okay, what about this?
Trigonal planar.
Nope.
No?
Wrong.
I'm trying to figure it out.
Oh, wait, because nitrogen will have nitrogen.
Reasonable guess. I see where you got that.
Oh, it's
Seesaw.
electron geometry.
It's a seesaw.
No.
That's T-shaped, right?
Nope.
It's not T-shaped.
I drew a T-shape, but that's not what it actually is.
But
It
it's
would
not a
be
nitrogen.
It's not a
it's
seesaw.
another-
You need 4 legs to make a
Oh, it's
seesaw.
electric, oh my god.
There's dots.
Yeah, so it's
It's tetrahedral.
Tetrahedral SP.
The electron geometry is tetrahedral. It's 4 things, 1, 2, 3, 4 things arranging themselves. It's that shape. SP3?
Mhm.
Yeah.
How do the two, so what's the answer?
This. I'm asking what type of orbitals are needed to make those.
Gotcha.
What, Chad?
How do the two electrons?
How did I know that? Because, well, we start by counting our electrons. If I look at the periodic table, nitrogen has 5. Hydrogen each has 1. 5 and 1 and 1 and 1 is 8. If I just make bonds here, that's only 6 electrons. I need to put 2 more somewhere else. They need to go on nitrogen because nitrogen needs 8 to be stable. Yeah. Okay, so we got that.
The plus is irrelevant.
There's a plus sign, yes.
It can hold, it's one of those that can do the octet thingy, right?
Yeah, if it needs
Whatever
to.
it's called. You said fluorine has 7.
We should have 34 electrons. 8 plus 8 plus 8 plus 8 is 32, so I'm missing 2.
2 on boron.
2 on bromine.
So.
Seesaw.
trigonal
That's actually a
bipyramidal.
seesaw.
That's a seesaw.
Yeah, that's the seesaw.
Sure.
1 group, 2 group, 3 groups, 4 group, 5 groups.
Trigonal bipyramidal.
Trigonal bipyramidal.
SP3D.
SP3D is what type of orbitals we're working with to make those. Okay. I already know the answer to this next one. I'll let you work on it. I'm gonna work on the next one. Wrong color, whatever.
Are most of them tetrahedral?
A lot of them are gonna be, yeah. SP3, SP3D? Eventually, this all just kind of boils down to like just counting the electron groups and matching it over, so. But the explanation of why that works is like the whole hairy part. Okay, questions? Okay, we'll do some practice. I got a worksheet. How much time do we have in class?
30 minutes.
I'll hand it out. We can work on it tomorrow as well. And we'll continue to unpack this. We still need to figure out how multi-bonds work. And then, yeah, and then there's another theory past this. This is valence bond theory, and this theory does not explain stuff. So I need to show you some more problems with this theory, or the next one, that is the best one. But it's the most complex, so. Good stuff. And then we'll have a test. It'll be great.